Hello, this is Dr. Muhammad, and this is the design of steel structures according to AISC beam column. Still, we are under this title, and today I'm going to talk about the AISC methods of analysis for required strength, and I'm going to talk about the moment amplification method, and then I'm going to wrap up with an example. So we are having, as we can see here, these are the main contents for today's video. And still we are, if you didn't catch or if you are not familiar with the beam column, I strongly recommend for you to revisit the previous video. Before that, it gives an introduction to the beam column and gives you the interaction equation and how AISC is dealing with the straining actions related to the beam column. So before going into this video, please revisit the previous video to understand and have good background before indulging into this video contents. Okay, let's go directly to the first part, which is related to the methods of analysis for required strength. AISC or AISC is giving and providing different methods for the analysis. It is important actually, and many maybe like engineers and students, they are overlooking these methods, but they are providing, or AISC is providing these methods only for the sake of simplicity and making the analysis to be easy for you in case of considering the P delta effect. Before going into these methods, I'm not going to give the details of the methods, just I'm going to highlight the main guidelines or the main outlines of each method, and then I'm going to talk about the moment amplification method, one of them. But the idea is that whenever that we have a beam column, okay, we have like different, as I said, straining actions that is going to be there, existent there under or for this element. And we mentioned that there might be geometric deformation for the axial for this element that is going to make deflection at certain parts of the element, and we are going to find that our moment that we are using is not representing the actual moment that is the cross section is receiving. So we found that we need to make another type of analysis that is considers this additional moment that is going to occur. Okay, so based on this idea, the AISC tries to find or tries to give to us some methods of analysis for obtaining the required strength. Okay, again, remember well that we were talking about required strength and the numerator and available, okay, available strength, okay, in the denominator. If you revisit the previous video, you will understand what I'm talking about. So the required strength here, commonly we are obtaining it from the load combinations, right? But again, sometimes these load combinations, they are not taking into consideration the additional moment that is going to take place due to what we call it the P delta effect, as I'm going to explain later. But there is additional things that we need, or additional amplification of this moment should be taken into consideration. So here I'm going to highlight what are the methods that AISC is providing for obtaining this required strength. Okay, so starting with this, or having what we have explained, understood, and in our mind, then we are going to find that we need to understand what is the meaning of the secondary moments. The presence of axial load produces secondary moments, and unless the axial load is relatively small, these additional moments must be accounted for. this is what we need to highlight here. If we are going to have loads on the element or on the frame, for example, that we are having here, and these loads, if they are going to produce small axial loads, then we can neglect any additional like bending or extra or secondary moments that is going to be there. But if we are going to have the axial load to be large, then we are going to find that there is a deflection that might take place and would occur even if the end conditions of the element is restrained against lateral movement. And also, if we are going to find that the cases where that our frame is not restrained against lateral movement, in this case, so one end is going to move relative to the other end. This would make a large delta that is going to take place across this element, in addition to the small delta that is going to be produced due to the axial forces on the element itself. So we found that we need to take these secondary moments into consideration. There is something is going to be developed. So it is not enough for us to take only like the P ultimate only or M ultimate only, okay, for the required strength, but we found that these actions are going to produce extra and secondary, okay, actions, especially related to the moments, okay. And the behavior that is usually there is, if we have axial force, as you can see here, on pin-pin condition element, as you can see here, and we have lateral loads, we found that the elastic line of this element is going to be displaced laterally, as you can see here. The maximum is going to be at the middle with small delta. And we can, by some differential equations and mathematical stuff, we can obtain how much exactly that is going to be there based on the end conditions and the type of loading and so on. So, and the inertia of the element and so on. So there is a differential equation for the derivation of the maximum like amplitude or the maximum amplification factor that we are going to use. But anyway, I'm just laying down here the main important idea. So we have two different types of P delta, which means that P delta means that there is an effect of the axial forces on the elastic line of the original element that is going to produce lateral displacement at several points along the element, and it's going to be maximum at the middle. We call this small delta. So we call this P delta, which is local P delta, where that the end conditions or the ends of the elements, they are not going to move relative to one another. This is the brazed condition. And the unbrazed condition, where that we are going to have one of the ends move relative to the other end, there is large, okay, we call it this is the delta, okay, this is small delta, this is large delta. Here we call this global, means that it is due to relative movement of the end of the element itself. Okay, this is the main idea of why we are going to consider this secondary moment. So there is some deflection here, okay, and this deflection is going to produce additional moment. If we multiply this P by delta, P times delta, it is going to give us moment here. And if we multiply this P by this large delta, it's going to give us additional moment here, right? So we need to take into consideration this moment, okay, in our analysis. Okay, moment amplification. For all but the simplest of structures, a computerized frame analysis is required to obtain the bending moments and axial loads. And this is true because we are using softwares now for obtaining our required moments and axial loads. The analysis gives the required strengths of member. Okay, so it gives the required strengths of the members or of members generally, which is in terms of bending moment and axial forces. That's common. As I said, there are two things here. We have something called available strength and another thing we call it required strength. Available strength means that the resistance of the element. The available strength of compression members takes into account member out of straightness, okay, and inelasticity. That's right. We have explained about it many times before, and I have justified the meaning of out of straightness and inelasticity, how they are being considered in the available strengths of compression member. The analysis, however, the analysis for the required strengths in our case for beam columns here should account for three different things, which is the displaced geometry, as we have said here, something like this, for example, and the member out of plumbness deviation from the vertical, which is the local one that we were talking about. This is delta if we have P here. And the third one is inelasticity. Inelasticity. So we have like three things that we need to take into consideration, or the analysis should take them into consideration in order to obtain the required strength. In order to obtain the required strength. Okay, I hope that everything is clear for you now. Okay. Now let's go to the ordinary structure analysis methods that we usually use. We have two types of analysis methods generally that we are using our softwares. The first one, we call it first order methods, and the second is the second order methods. So in the first order method, ordinary structure analysis methods that do not take the displaced geometry into account are called first order methods. So this is what we call it first order. In short, displaced geometry here means P delta effect. They are not taking into consideration P delta effect, P delta or P small delta. So whenever I say P delta, so remember that both, okay? So that's the point here. This is the first order. As we said, this is not right for us because there is additional required strength needs to be accounted for. And there is another type of analysis method, we call it second order methods. And these are like iterative analyses that account for these effects. Okay, iterative. They are going to be iterative. The point that I should have highlighted here is in the derivation or the equation that is we are going to use for the derivation of the amplification factor, for example, you're going to find that whenever that you use the load, the original load P, it is going to make the elastic line to buckle like this. And there is additional moment that is going to be applied, which is P delta. But this P times delta is going to add additional straining action on the elastic line of the element. So we need to increase it a little bit, right? And this is starting from the beginning when the element is displaced here and here and here. So this phenomena or this equation is going to be, or this concept is going to be nonlinear in itself, because we need to solve based on knowing the deflection at each point and consider P and the deflection, and then we are going to amplify the moment. This amplified moment is going to increase the lateral displacement and so on and so forth. So we need to know always delta. What is delta that is going to be there under different loading conditions, and then we are going to use our differential equation to get the maximum, okay, which is at the middle. So this means that we need, this is why we call it here iterative analyses needed for the second order, and this is actually something using numerical methods the already algorithms and the softwares, they are providing the iterative analyses in order to obtain the effect of the P delta. So we call this second order method. So you need to know whether that you are using first order or second order. In every software, you are going to find they are giving you the two options. Okay. So let's go now to the code specifications analysis methods, and let's go to the part that is related to us and the scope of our work here. AISC Specification Chapter C, you can have a look on it. Design for Stability. It's a very important chapter and many people, they are overlooking it, but really it is an important one. Provides 3 approaches for determining the required flexure and axial compressive strength. So it is giving us 3 different methods, okay, for obtaining or determining the required flexural and axial compressive strength. The first one, we call it direct analysis method, and the second is the effective length method, and the third is the first order analysis method. The first order analysis method. So we have 3 different methods here. Okay. I'm going to give, as I said, only highlights, because giving the explanation of each method is not going to be in the scope, or it's not covered by the scope of this course, but this is, I think, enough for us to understand the main idea of each analysis method. The direct analysis method is a second order analysis. So again, second order analysis. So the word direct analysis method in AISC, it means second order. Okay. Now we understand what is the meaning of second order, right? It means that it is taking into consideration the amplification of the moment due to the lateral delta. Okay, so the word direct analysis method is a second order analysis method. It's not a first order. That considers both P delta and P delta. So P small delta and P large delta, like, or lowercase and uppercase in Latin or Greek or whatever. Okay, so as an alternative, an approximate second order analysis is given in Appendix 8. So we need to visit Appendix 8. I'm going to show to you the index in a minute. Can be used. Okay, so here we need to use this direct analysis method, but there is an alternative for us, which is an approximate second order analysis, is given in Appendix 8. Okay, we can use it. Okay, this approach uses amplified first order moments and axial loads. So what is the meaning here? The key word here is amplified. So we are going to use the original moment, which is coming from the first order, and then we're going to multiply it by some factor. Okay, we're going to multiply it by amplification factor. We call it amplification factor. So this is one way. Okay, this approach uses amplified first order moment, amplified first order moment, and axial loads. Both the second order analysis and the approximate second order analysis are considered direct analysis methods. So we have like direct analysis, okay, method. This is the first method. So we have like 2 ways. Okay, the first one is, we call it second order analysis. Second order analysis. I'm going to call it like this. Second order analysis. Okay, and the other one is approximate. Approximate second order analysis. Okay, so both second order analysis and the approximate second order analysis are considered direct analysis method. They are under the same title. Okay, so we have, this is the main method that we should use. This is an alternative method that you can use. This is in appendix. As I said, this is in Appendix 8. Or you can use the first, which is the the second order analysis method directly. Okay, that is given. Okay. Okay. In the direct analysis method, member stiffness are reduced. So generally, we are going to reduce member stiffness. This is in general. Okay. For the direct analysis method, we are going to reduce the member stiffness. And we're going to use an effective length factor, K equal to 1 is used. Okay. So there are two things here. First of all, the inertia is going to be reduced, and in the same time K is going to be taken as 1, and an effective length factor of K equal to 1 is used both in the analysis and in computing the available strength, because we have two things here. Because analysis, it is related to the required strength. Available strength is going to be used, and as we are going to use it from chapter 4. Okay, so this is the direct analysis method. Maybe you are not fully understanding it, because as I said, you need to know the conditions only to be used. It is no need for or it is not in the scope of this course to like explain this in detail. Maybe I can give one video, for example, for the direct analysis method, the ways, the two ways, whether the second order or the approximate second order. But anyway, this is the conditions that you need to keep in your mind when you are dealing with the direct analysis method. Okay, and this is what you can see here in specification AISC 2010. You're going to find that this is Appendix 7 and this is Appendix 8. And in Appendix 8, you're going to find approximate second order analysis. So it gives to you the approximate second order analysis. Okay, and this is, as I said, where that you are going to find the approximate second order analysis is going to be used for here. This is in 2010 version. Okay, in 2016 version, they put it like this: approximate second order analysis. Okay, they put it in this way. It seems to be like maybe shorter. Okay, but here they were like giving it in the index in this way. But anyway, I think they are like the same. I didn't compare actually the two, 2016 and 2010. I'm not sure if there is slight differences or not. But anyway, I think that they are maintaining the same or the main theme of the approximate second order analysis. Okay, let's go to the second method, which is the effective length method. The effective length method. In this effective length method of analysis, it is covered in Appendix 7. It is covered in Appendix 7. Covered in Appendix 7. It also requires a second order or approximate second order analysis. So it requires second order or approximate second order analysis. Computation of the corresponding available strength, okay, has been discussed in chapter 4, which is compression members. As the name implies, an effective length factor K must be determined. So K here must be determined. It's not 1 as we said before in the direct method, okay? And the member stiffness are not reduced. And I, which is the member stiffness, they are not reduced as before. So take care. These are the two conditions that you need to take care when you are talking about the effective length method. When you're talking about the effective length method. Okay, this is in Appendix 7. If we go back, we're going to find it here. This is in 2010, the specification, 2010. You can find it chapter 16, the manual. Okay, you're going to find this is Appendix 7, and they are giving you the effective length method as the name entitles. You have three different parts here: limitations, required strengths, available strengths. They are giving to you what are the limitations that you should take into consideration, how to obtain required strength, how to obtain the available strength. This is in 2010 version. For 2016 version, you're going to find the same also in Appendix 7, effective length method, page 568. Okay. Remember the two conditions that I have mentioned about them. Now the last thing is the first order analysis method. The first order analysis method. Let's go back here. We said that we have the direct analysis method, the effective length method, and the first order analysis method. And the first order analysis method is a simplified version of the direct analysis method. That's true. It is a kind of simplified version of the direct analysis method, which is method number 1. Okay, that can be used when certain conditions are satisfied. So we have some limitations, not limitations, but there are some prerequisites or like conditions that needs to be met first in order to use it. So it is considered to be a good option for you if these conditions are satisfied. It is covered in Appendix 7 for this is the same also in Appendix 7 as we have mentioned here. Yes, 2010 Appendix 7. So you can find it here, first order analysis method, and also in 2016 version, first order analysis method, still they are using it. Okay. For the available strength and effective length factor K equal to 1 as used, member stiffness are not reduced. So in this modified or simplified version, we use K equal to 1 as the case of the direct analysis method. However, for the member stiffness, they are not reduced. Okay, they are not reduced. This is maybe the difference between the two, first order analysis method and the direct analysis method. Okay. Okay, now let's go which one that we can use and what is the if there's some hints about all of them, about all of these methods. Hints about the methods: all columns in real structure are subject to initial displacements that result from member out of plumbness. Okay, which is something, if we have the member like this, the element itself is not straight. Okay, maybe it is having something like this. So this means that there is a kind of out of plumbness. Okay, in reality, in each of the 3 analysis methods, member out of plumbness is accounted for by including fictitious lateral loads. Fictitious lateral loads called notional loads in the load combination. So this is all of them, they are doing the same concept in order to take into consideration what? Out of plumbness. That's the idea. So fictitious lateral load, or we call it notional loads, that is going to be used in the load combinations in order to take into consideration the out of plumbness. Which method is the preferred? The direct analysis method is the preferred and most commonly used, actually. If the appropriate software is available, a second order analysis is the method of choice, of course, because you have your software, so second order analysis is going to be the best choice for you. If a second order analysis is not available, the moment amplification method, which is an acceptable direct analysis approach, can be used. So we are going to use, in this case, we are going to use the effect of the second order is going to be used through what we call it the moment amplification method, okay, which is an acceptable direct analysis approach, can be used. And we are going to talk about this. Okay, we are going to talk about this. Okay, the moment amplification. The moment is going to be multiplied by an amplification factor, and this amplification factor is going to give us the effect of the second order. If the bending moment and axial force are from a second order analysis, so this means that already we have the bending moment and axial forces coming from second order analysis, means that no need for you to bother yourself. Okay, from a second order analysis, okay, you can go straight to the interaction equations from AISC Specification Chapter H. Okay, you can go directly for this, because already your moments, okay, and bending moments and axial force, already they are augmented, already they are amplified. by taking into consideration the second order analysis. Okay, so this is the condition here. If not, if your bending moment and axial force are not considering second order analysis, so if the required, in this case, if the required strengths are from first order analysis, means that we didn't take into consideration the second order analysis, the moment amplification method, which I'm going to talk about it, and approximate second order analysis given in Appendix 8 can be used. We can use it, as I said in the previous slide. Okay, and this method is going to be covered in the following sections. Okay, because this is like the most common, historically most common method for considering the P delta effect, the moment amplification method. Okay, so let's go now and talk about moment amplification method. The moment amplification method entails computing the maximum bending moment resulting from flexural loading, and take care of the word flexural loading here, which is coming from transverse loading, whether that you have transverse loading that is being applied directly, or due to, if there is no transverse loading, but due to some like moment at the ends of the member, so or member end moments, both of them, they are going to be considered. Okay, so any moment that we are going to have. Okay, so flexural loading, transverse loads, or member end moments by first order analysis. So it is considering first order analysis. Then multiplying by a moment amplification factor to account for the secondary moment. Okay, so as I said, we are going to find M node and then we're going to multiply by factor. This factor is what we call it the moment amplification factor. It takes into consideration the effect of the eccentricity that is going to take place on the elastic line of the element due to the axial forces and the bending moment, the transverse loading, if we have transverse loading, for example, or the bending moment at the ends, as we are going to see in different cases. Okay, so it is used because it's simple actually. Our main focus is how we can obtain this delta. That's it. And we are not going to make any second order analysis. It's done for us because we are going to amplify the existing ones. Okay. Okay. Now let's go and see how we can obtain this magnification or moment amplification factor. Actually, it has a derivation, and this derivation you can find it in the textbook. I'm not going to bother you with the derivation. It's clearly stated in the textbook. You can find it if you want to know how the differential equation is being derived and solved after that. So it's not our main focus, the mathematical part. You can find it in the textbook, but our focus is the significance, how we can obtain, how we can like implement what kind of amplification factor in the type of the moment that we are having. So in general, this figure is illustrating for us what we are doing here. So if we have P ultimate axial load is being applied, and we have M node, which is original moment at the ends of the member, they are the same here. There is delta, small delta here. Small delta is going to take place here. Still, the ends of the element, they are not moving to one another. Okay, it is like local P delta. Due to these end conditions and the loading that is being applied on the element, we're going to have moment here, M node, which is going to be constant along this element, and its value is M node. However, this P delta effect is going to increase the moment at different sections along this element, and the maximum contribution is going to be at the middle. So we're going to superimpose the moment coming from this delta with the moment coming from the original loading condition. As you can see here, this is the rectangle coming from the original loading, and this is the part of the of the circle, or whatever the elastic line curve here, which is going to be P ultimate delta. The total moment here is going to be m node plus P ultimate delta, right? So we are going to increase the original moment, which was the end moments, with something here, okay? Some amount of moment. So instead of that, we are going to make it like this. So this both, we call it like M maximum, right? So we say that we're going to claim that this M maximum is going to equal to M node times something, factor. We're going to put here factor, the amplification factor. This equation, or this amplification factor, this is what we are going to try to derive here. We found from the derivation of the equation, the differential equation and so on, that M maximum is going to be like this: M node times this amplification factor. From the derivation, using the eccentricity into consideration and Euler loading into consideration and the P, the original loading, into consideration, after rearrangement of these stuff, we found that at the end we have 1 over 1 minus P over PE. Remember, PE is what? Euler, the Euler buckling load. The Euler buckling load, which equals to pi squared EI over L squared. It takes into consideration the material, represented by E, the cross-section of the element, represented by the inertia, and the length of the element, represented by L. You're going to ask me where the end conditions. Euler load is talking about pinned end condition, okay? So here, this is how the amplification factor is going to be formulated. 1 over 1 minus P over PE, okay? Where M node here is the unamplified maximum moment, which is, as we said, the unamplified. It is the original moment here. We call it original moment or unamplified maximum moment. In this case, it results from initial crookedness, okay? In this case, it results from initial crookedness. But in general, I mean that here it was original crookedness. Actually, this is from the textbook itself, when they were like deriving the equation itself, okay? But anyway, this amplification, but in general, it can be the unamplified maximum moment, okay, is going to be, it can be a result of transverse loading. If we have transverse loading, for example, if we have something like this here, or end moments, as our case here, okay, or end moments. So the unamplified maximum moment, which is M node that I'm talking about, then it can come from transverse loading, end moments, or like the initial crookedness, if we can talk about it, okay. The moment amplification factor is, therefore, this is the part here, 1 over 1 minus P over PE, okay. Based on that, because the member deflection corresponds to a buckled shape, take care of this P here. P, it is what? The load that is being applied. But our failure mode here is going to be buckling failure mode, right? Buckling failure mode. It means the limit state of buckling. This requires or necessitates that this P should be near to the failure. So we are going to use as P ultimate loading, okay? So because the member deflection corresponds to buckled shape, we're talking about member deflection, so this means that we're talking about buckling failure mode, corresponds to a buckled shape. The axial load corresponds to a failure load, that is a load corresponding to an LRFD formulation. So we use P ultimate in this case. So in the amplification factor, this P, because we are talking about buckling failure mode, we need to let it P ultimate. Okay, understand? So this is the justification of using P ultimate. Okay, if I ask you why we use P ultimate here, because the member deflection corresponds to buckling failure mode, to a buckling shape. Okay, so the axial force should correspond to this failure mode, which is, it's not B service loading. No, it should be P ultimate loading. Okay. Okay, now I think that we are ready now to go into an example and see more about it. Okay. Okay. So now we're going to find this example in the textbook also. Use expression 6.7 to compute the LRFD amplification factor for the beam column of example 6.1 that we have explained before. Okay. The expression here 6.7, it is related to the amplification factor, which is 1 over 1 minus P ultimate over P Euler. Okay, this is the amplification factor. This is the amplification factor. Okay, since the Euler load PE is part of an amplification factor for a moment, it must be computed for the axis of bending. So we need to calculate this PE first, which in this case is the x-axis. So we have like, this is the cross section. Okay, if you visit this is x. Okay, so we are going to get PE around this x-axis. Okay, if you revisit example 6.1. In terms of effective length, the Euler load can be written as, so PE equals to pi squared EI over KL to the power raised to the power 2 or squared. Everything is known for us from the previous example, and it's known for us. The Young's modulus is 29,000 KSI for steel cross section. It is known for us because we used it from example 6.1. Okay, because I remember that it was W10 by 49 if I'm not wrong. So let me check this. I think that it was like that because this is what we used in the, sorry, yes, this is in the previous video, I guess. Yeah, this is 6.1 here, and this is what the cross section is. We are talking about W10 by 49. Okay, so everything is known for us here, and we can get all the properties of this section for our case. So I think that here in this in our method, we are going to, in our example, this I is given already for W10 by 49. If you want to check, you can stop the video here and revisit the properties table, and you can obtain the inertia around X. KL, it is 1 by 17. Already we have mentioned about this. It was pin-pin condition as far as I remember, and this was 17 feet. K, it is 1 because we have pin-pin condition. 12, it is the conversion from foot to inch. So we have 12 inches in 1 foot. So it is raised to the power 2, and then we have this is PE. What is PE? It is Euler buckling load. It is the buckling load that is going to be there under pin-pin condition. So if we apply 1871 kips on this loading, we're going to find that it would start buckling. From LRFD solution of example 6.1, please revisit previous video, and you are going to understand what is the meaning of P ultimate equal to 200 because we have P ultimate was applying, here we have dead load and live load. So please stop the video, revisit the previous video, and you are going to understand what is the meaning of P ultimate here. Okay. Okay, and then we are going to substitute in our equation, which is going to be 1 over 1 minus P ultimate over PE, and we have P ultimate to be 200 from the previous example, and PE is going to be 1871 or 1871, then we can put this here. Okay, I mean that we can, the ratio here is going to be 1.12. What is the meaning of this? 1.12. This means that 12% is going to be increased, or we are going to amplify our original moment by 12%. So we're going to multiply our moment by 1.12 times M ultimate to obtain the amplified moment due to the P delta effect. Okay, due to P delta effect. Let's clear everything here. So this 1.12 means that, which represents a 12% increase in bending moment. The amplified primary LRFD moment is 1.12 times M ultimate, which is 107.1. Okay, already we have explained it before. And then this gives us 120 foot kips. The amplification factor is going to be 1.12. Okay, so this, I think that by this we are going to, this is the end of our video for today. I hope that you have understood what I have explained, and I hope that you have an idea now of what are the major and the main methods related to the analyses in order to obtain the required strength. As we said, we have direct analysis method, effective length, and first order analysis method. And we mentioned about every one of them. All of them, they are highlighted, okay, in the recent AISC 2016 in Appendix 7 and Appendix 8. And we mentioned that all of them, they are like dealing with the same idea of having fictitious lateral load and notional loads there. And we mentioned about what are the preferred, or what is the appropriate selection for you based on the available software that you have. And we mentioned about the moment amplification method and how we can use it, and the derivation of it, and understanding how we can use the amplification factor. And we have ended with an example for this. More and more is going to be explored and investigated in the next videos for the beam column. Thank you very much, and see you in the next video.